Yeah. Yeah, you're going to become famous, Einstein. 1,000 years from now, you'll be like the remnant of human civilization. People can still find. Yeah. That bit of video from, yeah, September. Yeah, okay.
So through there.
We can try that. Okay, so we're going to try a new kind of, let's see. So, okay. So you want to plug this in? Great. Ah. Okay. So,
Have to switch your audio devices and expect.
yeah, it switched it automatically last time. Do you?
Okay, just hit the up arrow by your mute button there. There's a little carrot there, the up arrow. Down a bit, and to your right a bit.
How are you?
There you go.
I'm good.
Okay, we're good. Great.
Oh,
Okay, yeah, it's a USB for both. Yeah, yeah. So we're good.
I will pack up and get out of here.
So it's all set
It's
up.
all set up. So
Cool.
Back up. You just have to unplug the power and the USB.
Right,
Just stick them both in the back.
right.
Put the lids on. There's just 2 latches on each.
Right.
That's it. The microphones can go back into the bin there.
Okay.
I'll take this away and store it.
Right.
And all those cables and stuff can go into that bin as well. They don't have to drive around in cardboard.
Right. Right.
Moving style.
Yeah. Okay. So yeah, and do you want to write a new set of instructions?
Yeah, we'll do.
Yeah.
And those 2 long cables there, the power cables,
Right.
you can actually use those with your lights.
Okay.
So if you want to keep those,
Cool. Yeah,
it might be a
sure.
good alternate use
Sure.
for them.
Yeah. Yeah. Excellent. Okay. We will do that. Totally good. Okay. And if you want, you can turn that so it shows a view of you. You can turn this computer so it shows the 2 of you and the others who come in more interesting view than what it's showing us. Yeah. I know, dog. It's very hard to figure out the human motivation here. For what we're doing. Yeah. Okay. Great. Well, thank you very much. Oh, wait. There's something I forgot.
Thank you very much. Okay. Have a great day.
Great. Thank you.
Sorry.
All right.
Pass here. Thank you so much.
Okay, cool.
oh, you might have grabbed the wrong one. Yeah, but I think that one's for like a whole different. That one was for the different, because that one's for the one that's labeled blue.
Yeah.
That one had a specific.
Yeah. Mhm.
What's the dog's name?
What? His name is Einstein, and he was named by the followers I have on my Instagram channel. And my Instagram channel is much more interesting than you would think, because a 25-year-old musician runs it for me. And if you direct message me, she will answer. And she doesn't seem to ever make mistakes. Yeah. Okay, cool. All right. Thank you. Thank you, Angus. Yeah. You too. Bye-bye. Yeah, I brought that check and I almost forgot about it, but it's been a pretty disappointing trip for him. Yes. Still left holding the bag kind of thing. Okay, so now let me put on my headphones. Okay, so.
Sorry, may I? We didn't get the lecture slides yet, right? Or there was none shared.
What?
There's no lecture slides, right? Like I'm just not missing anything for today.
What there are there are two wireless. Sorry, what were you?
Is there a PowerPoint for today that was shared at all, or?
No,
Okay.
he has not shared the PowerPoint.
Okay.
You'll get the PowerPoint later.
Not yet.
Okay. All right. Okay, it's all yours. So,
Okay,
yeah.
let me move my things here. Share. Okay, do you see my screen?
Yes, yeah, looks
that better?
great. Yep.
Well, good afternoon, everyone. If you can hear me, then I can start.
Yes, we hear you well.
Can you see my slide?
Yes.
Well, good afternoon for those who are on campus in the classroom, and for those who are online, like me. As you can see, I have long hair. I don't know if you can see me. I don't even leave my dungeon here. So I never go outside, and therefore I didn't go on campus yet. It's been almost a year I haven't been on campus. Crazy. So I'm Osmar Zaiane. I'm a professor in computing science. I'm also the former director of Alberta Machine Intelligence Institute. I highlighted former because people still think I'm the director. I've been the director for 12 years, and now somebody else is taking that leadership role. I'll be with you for 3 lectures, so 3 parts. Today, we'll be talking about AI. What is AI, the past and the present? To better understand some terms and why and what's the role and things like that. In the second part, we'll be talking about the future. Should we worry about the future? Since this lecture is about promises and perils, what are those perils? And part 3 will actually come back down to earth, and I'll talk more concretely about how machines learn so that, well, they do intelligent kind of tasks. But first, let me demystify or remove some doubts about some misconceptions. It is largely believed that computer scientists and particularly people in AI assume that human intelligence is more or less solved and that machines will soon replace humans. Well, this is definitely not true, even though duplicating some form of intelligence equal or even superior to ours is one day inevitable. Human intelligence is more complex than many would think. We thought it was easy and then realized it's actually more complex. Yes, with the new paradigm, like you certainly heard of deep learning, and I'll talk about deep learning later on, we can make the machines do amazing things that seem very clever. But deep learning, which is today stealing all the attention and has the limelight on it, is still very limited compared to sentient human beings like you and I. An alien, an imaginary alien on the TV series Star Trek, The Next Generation, said, humans are bags of mostly water. I don't know if you remember that quote, where we're actually a bag or a ball of emotions, and our actions are not just dictated by our brains, but also our hormones, our microbiome in our guts have a say in the way we behave and make decisions. We are not always rational, but function. Let's say in a smart way, in an astute way compared to other animals. We reason. That's not to say that animals don't reason, but we follow very mathematical, logical rules. I believe if we do not self-destruct before we reach that point, because we are actually vicious and selfish animals, we will eventually build and have a machine that is as intelligent, if not more intelligent than us, the humans. But in my opinion, unless we have some major breakthrough soon, we are still far from the moment, that particular moment in the future that we call singularity. At least I don't believe that I will see it unless I live for a long time. So I'll give you a very simple, I'll give you a very simple example. Humor. If I say all humans are intelligent, but some are asymptomatic, I don't hear anybody laughing, but that's a joke. It's a joke that I'm basing it on the pandemic that we live today. So some people get sick with COVID-19 and some people are asymptomatic. Well, it's the same thing with intelligence. Well, humor. Is there a question or just?
No, they're just dealing with hybrid technology.
Okay.
Yeah.
So,
but they're solving things. Yeah.
good. Oh, we'll talk about solving indeed.
Yeah.
So humor is one of the most sophisticated forms of human intelligence. It requires semantics, interpretation, knowledge, culture, and timing, when to say the joke. I mean, like I gave you a joke and nobody laughed because the timing was not right, I guess. So computers don't understand humor. They can't create or even recognize jokes yet, particularly sarcasm. Sarcasm is very hard, even for humans. This being said, we are making incredible strides in that direction. As someone in AI, in the field, I can feel this acceleration. I mean, we are changing and improving on a daily basis. We are making these contributions and innovations on a daily basis. At the same time, we're also discovering and realizing the complexity and the sophistication of the human intelligence. We don't know it very well yet. We're still discovering how complex even the brain is. So let me start by this reflection. What you see here is a photograph of the Wright brothers when they made their first flight. This was in December 1903. Now, this is a picture of Neil Armstrong walking on the moon. And in July of 1969, we had our first flight to the moon and back with humans. So between these two pictures, it took just 66 years between the first successful flight of a powered aircraft with the Wright brothers and the first manned flight to the moon, which is amazing. And now, actually, we managed 52 years later to fly a helicopter on Mars. So it took only 118 years to fly on a planet besides Earth. And just let it sink in for a while. This is just a century. And we went from flying a few feet above the ground to flying on Mars. What is 100 years? Is nothing. 118 years is nothing in our existence here on Earth as a species. And in terms of the life of Earth and life on Earth, this is nothing. So it shows you how, and we are taking it for granted, it's going at an amazing speed. And this is not just for aeronautics. This is in all fields, including medicine and computing. And now, does this inventive spirit of discovery, taking risks and dreaming require intelligence? What is this intelligence? And are only humans bestowed with this intelligence? Intelligence is defined in many ways by different people. There's no standard definition. And actually, even in psychology, there are theories with an S of intelligence. Some researchers have suggested that intelligence is a single general ability that humans have, or I guess don't have. Others believe that intelligence encompasses a range of aptitudes, skills, and talent. Is it specific to humans? And how would we define intelligence? So let me show you some examples here. This is a dog in the kitchen. I don't know if you can see the video. The dog is smelling something nice. It smells better than the dog food that he gets every day. So he's looking for it. It comes from there. I can't reach. So it's reasoning, it's thinking, going around. What can I do to get to that source of the nice smell? Well, I have a problem. I have to solve it. So I'm solving. Dr. Solez was talking about solving problems. Well, this dog is trying to solve a problem. The solution is to push that chair. I am checking. Oh, I have another problem. I can't get up there, the counter. How do I solve it? This is a sub-problem. I'll solve it by jumping twice. Oh, I got there. Now I found the source of the smell, but it's hot. I can't touch it. I can't get in. Now another sub-problem. I'm going to solve it. It's too hot. Another attempt with another paw. It's thinking, how can I solve this? This is too hot. I can't put my head in there. Just grab it and throw it on the floor. There you go. Problem solved. Is that intelligence? Well, maybe that's a dog. If the dog learns from us, watching us, or things like that. Well, let's see another example. Probably saw this video. This is, well, it's the collective together to go and reach the wasp's nest without jeopardizing, because the wasps actually can kill the ants. I mean, how they manage to defeat them is very impressive, but there's some kind of reasoning that happens behind it. Maybe not these ants, but all the generations put together. We still don't understand. We still don't know how this happens. I actually have other examples with intelligence of the ants. Yeah, I'm going to stop it here. So how do you understand? So how do you, how do you define intelligence? I want to turn it to you guys. I don't know how many people are in the room and how many people are connected online. But who would like to volunteer a definition of intelligence?
Yeah. Do you want to move the microphone over? So there are 7 students in the room. And they have their own microphone, which are going to be used right now.
Hello, my name is
Hi.
Chun, and I guess the definition of intelligence that I would volunteer is the ability to think creatively and solve problems on your own.
Think creatively and solve problems. Yeah, I like that.
Okay, who else?
That's good.
My name is Matthew. I might extend that a little bit further. I would say it could be applied to observational learning and being able to use deductive reasoning to see a situation and then be able to solve problems based on your environment around you.
Yeah, so we saw that with the dog, looking at the environment, observing the environment and finding problems and solving those problems. Yeah. Creatively pushing that chair. That's amazing, actually. Yeah.
Yeah, I'd like to add on to that. And I think it's not just like solving the current issue, but it's also learning from your past experiences and applying them to this current situation.
Learning from the past and applying that by analogy to the present. Yes. Yes, I like that. Any other definition? Hey, you guys are great. It's amazing.
I think intelligence can also include like the emotional aspect and wanting to satisfy your like drives and motives and those kinds of things.
Yes, emotional. Actually, we talk about emotional intelligence. Yeah, that's EQ, not IQ, but EQ. That's true. Are those who are online, anybody wants to volunteer something, a definition? There's no right and wrong. So,
hi, I'm Rob, and for
Rob.
me, just adding on to this, transmitting ideas to further generations and helping them live better, and inventing culture, language, those kind of things would be counted as intelligence as well.
no, that's interesting, because when you look at the theories in psychology about intelligence, they encompass what you just said, and I'll get to that. Okay, so let me move this away. So intelligence, the etymology of the term, it comes from intelligentsia in Latin, and itself comes from the verb intelligere, which means comprehend and perceive. And in the Middle Ages, it was used, that verb was used to express understanding. So obviously, understanding and perceiving the world, and somebody was talking about observational learning, it's part of indeed intelligence. If you look at the Merriam-Webster's definition, intelligence is the ability to learn or understand or to deal with new or trying situations. And it's the skilled use of reason. So there's reasoning in it. I don't necessarily like this definition, but this is how these dictionaries are defining it. So the Oxford Dictionary is even worse. Intelligence is the ability to learn, understand, and think in a logical way about things. The ability to do this well. So doing it is not enough. You have to do it well to be considered intelligent. So for me, intelligence, I have my definitions. And then it encompasses what you were saying. I really like what you said before. So intelligence is the ability to acquire knowledge and to apply this knowledge or skill for the appropriate situation. And some of you have said learning from the past and applying it in the present. That's exactly it. There's also the intelligence is the capacity to learn, reason, and adapt to new situations. And intelligence is the capacity to change our environment to our advantage, to the betterment of our condition. And that's where the invention comes in. There's another definition from Wikipedia that I like. Intelligence is the ability to perceive or infer information and to retain it. So this is remembering, retaining something as knowledge to be applied towards adaptive behaviors within an environment or context. So adaptation is very important here. If I go to the theories of intelligence and psychology, there are many different theories, and I'm just talking about two here, the most famous ones. One is from Sternberg, Robert Sternberg. He's an American psychometrician, they call him. He was, and I don't know if he's still, a professor of human development at Cornell. He developed what we call the triarchic theory of intelligence. So there are three kinds of intelligence. There's the practical intelligence, there's the analytical intelligence, and the creative intelligence. And this is how they draw them, the triarchic intelligence, theory of intelligence. So the practical intelligence is the application of common sense knowledge acquired by experience to solve common problems. So you learn from experience, and then you use that by analogy for other situations. Analytical intelligence is the ability to analyze, evaluate, judge, compare, and contrast in order to solve a problem. For example, you solve one problem, and then by analogy, you apply it to other encountered problems. Not exactly the same problem, but you use the tools that you learned from the past. You compare, basically, this is the analysis and the evaluation. You compare this current problem with previous problems, and you do the contrasting analysis. The creative intelligence is the capacity to imagine new solutions to a new unexpected problem or situation. And one can be good in one intelligence is not as good in the other intelligence. They are not necessarily the same. This is the argument that Sternberg was providing. Now, there is another theory from Gartner. This is, Gartner is a professor of psychology at Harvard University. And he says that there are multiple different kinds of intelligence: linguistic intelligence, logical, mathematical intelligence, musical intelligence, bodily, kinesthetic intelligence, spatial intelligence, interpersonal and intrapersonal intelligence, and naturalist intelligence. They're completely different. And I'll give you some examples. Like I'm really dumb when it comes to music. I'm not a musical, I don't have any musical intelligence, but other people who are not very good in math or whatever, but they're incredibly good in music. They can distinguish between understand and appreciate rhythm and pitch and tone, and may play multiple instruments. I barely play guitar. Linguistic intelligence, you have some people who can perceive different functions of language. They may speak different languages. They may easily learn a new language. And same thing with bodily intelligence. You know, some athletes who can do amazing things, and we can't imagine how they do it. They do it, I don't know, because they have very special skills. So there's an argument there that there could be many different kinds of intelligence. Now, one interesting thing here is that this interpersonal intelligence and intrapersonal intelligence, some people have combined them both to define the emotional intelligence that one of you has referred to. It's the capacity to understand and express emotions. So you understand the emotion of the other, and then you express your own emotion and react to the emotion of the other. This is what emotional intelligence is all about. And computers are not there yet when it comes to emotional intelligence. Everything else we can try to mimic and copy. So this is with regards to what people think intelligence is. Now let's go to our lecture. What is artificial intelligence? The intelligence that now we consider artificial. I don't like the term artificial. I prefer saying computational intelligence. It's an intelligence that is computed. There's nothing artificial about it. Intelligence is intelligence. So I will also talk about what is machine learning, how machines learn, and why is AI coming now? Why are we talking about AI now more than any other time? And then I'll give you some examples. So that's basically the plan for today. So unfortunately, intelligence, people are not all like you at the university, and you can think. and try to come up with a critical kind of definition of what intelligence is. I'm very impressed by your definitions. I really like them. But most people get their definition from the media, what they hear on social media, on the movies and things like that. So they hear, well, AI market will be worth, I don't know, $60 billion in 2025. So obviously it's important economically. The one who dominates AI will rule the world. This is what Vladimir Putin has said. So it must be important. So we get our definitions, so the masses anyways, they get their definitions from newspapers or social media and certainly movies. And the movies, they do not portray a realistic picture of what AI is. And often they give us the wrong pessimistic view of what AI is. It's them, the machine, against us, the humans. They will destroy us. They are our enemies, which is not the right thing. It's not the machines against us. And then no, obviously now, because they're against us, so there's AI is an existential threat. AI is actually a tool and you're using it. You have it in your pocket right now. That's what AI is. That phone that you have in your pocket, this is the level of AI we have today. If you look at how the pioneers who imagined AI from day one defined AI, they certainly didn't look at movies to define it. They define it as the science of making machines do things that would require intelligence if done by humans. This is Marvin Minsky, one of the pioneers in the field, and he's the first. He's the founder of the first AI lab that was created at MIT. So artificial intelligence is a discipline striving to get machines behave intelligently by performing tasks that would normally require human-level intelligence. For me, artificial intelligence or computational intelligence is an enhancement of our creativity, is a tool. And artificial intelligence actually is a moving target. But we considered artificial intelligence yesterday and we achieved it. It's not artificial intelligence anymore. And what is artificial intelligence today is more complex than what it used to be yesterday. So it's a moving target. Yeah. So artificial intelligence is not new. When I was talking about Marvin Minsky, I said one of the pioneers. Well, actually, Marvin Minsky passed away just a few years ago. AI started in the 50s. So here's a picture here. In the 50s, after the Second World War, people were thinking, what can we do with these machines? And some researchers have speculated that if we take any human activity and break it down into pieces, each piece can be programmed by these machines. And when put back together, we can create intelligence. So they speculated that, and many people have believed in this idea, a very simple and simplistic idea. But for a long time, these researchers were funded by governments, whether it is in the United States, in Europe, or in Russia, especially during the Cold War, because they believed that the first one who reaches that will rule the world, like what Vladimir Putin has said recently. So there was a lot of hype, of course, a lot of optimism, very high expectation, and a lot of money flowing towards these researchers. And the research they were doing, they were showing how we can solve problems. We were talking about solving problems before, but solving problems that are considered tough, like, for example, playing chess or playing checkers, or games that we knew that, well, the common sense told us that those who are good at these games are intelligent, between quotes. But soon there was a disillusionment. We realized that was utopia. And AI was forgotten until the 80s. And in the 80s, there was a new subfield within the AI field, a subfield called machine learning. And machine learning is about making computers learn to do a task so that we don't have to program it to do that task. So it learns it without us humans, coders, computer scientists, coding it for that specific task. And I'll explain later how it works. But then the hope was revived. It brought back a lot of hope. And it created a lot of disruptions indeed in the field. Like here, I'm representing the spam detector. It's today completely automatic. There's another application that was phenomenal, is recognizing handwritten digits so that we can read automatically the addresses on the postal code, for example, on envelopes. You can read the amount of money on the checks. We don't have checks today. Actually, in Europe, they still exist, but checks were written by hand and a machine had to read it. So all that was done with machine learning. And it was very impressive, but not as impressive as the first promise in the 50s. But what happened is that in 2012, so around 2010, 2012, the subfield within machine learning called deep learning surprised everybody, because we were able to solve problems, and I'll get to that soon, but in some problems, the machines were able to surpass humans very rapidly, very quickly. It was very impressive. So now we talk about deep learning. Deep learning is based on a technology that existed from the 50s called neural networks. So it's rebranded as deep learning, and I'll tell you why a little bit later. So what you have to retain from all this is that in computing science, we have many fields. One of them is called artificial intelligence, but it's as important as database management systems, security, encryption, algorithms, human-computer interaction, networking, high-performance computing. There are many subfields in computing science. One of them is AI, and it's taught to undergrad students, actually, so important. I'm not putting it big here because it's the most important field. I'm just putting it big here because I'm going to zoom in and neglect the others. So inside artificial intelligence, there is a subfield called machine learning. It's one of the subfields, like planning, like knowledge representation, reasoning, computer vision, natural language processing. All these are within AI. But machine learning is also, I made it bigger here because I'm going to zoom in. There are many paradigms inside them. There's a supervised learning. There is what we call unsupervised learning, reinforcement learning, and others. And within supervised learning, they have different approaches. One of them is called deep learning. And there are many other approaches, support vector machines, assistive classifiers, decision trees, and so forth. One of them is called deep learning. So what you have to retain is that deep learning is a kind of supervised learning, which is kind of machine learning, which is a kind of AI, which is in CS. Okay, they're not synonymous. You will find in many newspaper articles that they talk about deep learning like if it was AI. AI and deep learning are not synonymous. Deep learning is part of one small part of AI. Okay, so deep learning is part of machine learning, part of AI. Okay, so there are other terms that you probably hear about. Data mining has been around for a while. What is data mining? Data mining is a process of discovering and extracting potentially useful and previously unknown patterns from data. Data mining is at the confluence of many fields, including machine learning and AI, because machine learning, the way we will learn, and I'll show you later, we try to find patterns in the data in order to create predictive models to do prediction. So in general, that's what data mining is also doing. It's the analysis and intelligent interpretation of large data. So same thing with machine learning. You look at data in the past, you experience, like you were saying, what is intelligence learning from the past? The machine will look at data which represents the experience from the past in order to provide actionable knowledge from this data for human decision support, or actually also automatic decision making. Automatic decision making looks intelligent because it's taking advantage of the data from the past. So as I said, data mining is at the confluence of many fields, including machine learning, which has neural networks and deep learning and so forth. There's another term that you probably hear about is data science. It's a multidisciplinary field that uses processes and algorithms to extract knowledge and insights from data. There's all, it's not just the data mining part of it, like we just defined it, but it encompasses also dealing with storage and management of the data, so the infrastructure in the company or the organization that is collecting that data. So data science, again, is at the intersection of many fields, statistic, databases, and computer science. And you can see, again, data mining here, machine learning here, they're all part of the big picture. So often synonymous to data mining, data science, data mining, and data analytics, business intelligence, big data, they all are unfortunately used as synonymous, but there are distinctions between them. Now, let's go back to AI. Why is AI so important today? And I just said that it existed since the 50s. Actually, the first conference on artificial intelligence, it was coined artificial intelligence in 1956. It's not new. So why this resurgence today, or at least in the last 10 years? Well, there are three main factors. One is the fact that we are collecting a lot of data. Every year we collect twice as much as the year before. So it's exponential. It's today free to collect any kind of data. Another reason is the high performance computing we have today. The computers are way faster than before, have more capabilities, and because we developed new powerful algorithms. Some of these algorithms, we developed them before, but we were not able to use them or push them to the limit because we didn't have the high performance computing we have today. So today we have the chance to do that. So these three factors put together allowed us to push AI further than ever before. So where's data coming from? Well, you probably know, so I'm going to focus on each one of them to show you now. This is a visualization of some sources of data that we are flooded by. This isn't in 2017, but it's the same today. I mean, the number of tweets per minute or per hour, the number of emails, the number of searches, all this is collected. Your behavior online is collected, but there are other data that is collected as well by different sensors. It's phenomenal when you look at the amount of data that is available to the public and to governments and to companies. It is unthinkable. It's huge. Just to illustrate this, so people can understand what it means that we have a lot of data. If we just talk about zettabytes, it doesn't mean much. So where's data coming from? It comes from different sources. Many of you are in medicine, data in healthcare. In healthcare, we're collecting a lot of data about patients, the procedures we do to them at the hospital, the conditions, the drugs we give them, the treatments, and so forth. All that is collected. So some people have tried to quantify, to put a number on that and visualize it. Of course, there's all the data coming from Internet of Things. It goes beyond that, what exists at the hospital, insurance providers, the clinical trials, genome data, social media. I'm just talking about medicine, but of course, the same thing is happening in e-commerce and e-gov and so forth, etc. So in healthcare, there was a paper in 2011 that was estimating the amount of data collected in the US in healthcare. They were talking about 150 exabytes, and they were saying we were reaching zettabytes. What does that mean? These terms mean nothing unless you put an image on that. So they tried to give an analogy. And in that paper, they were talking about taking that amount of data. This is in 2011. The paper was in 2011, but they based it on data from 2007. They said, we need that many CDs, and we're talking about CDs, that many CDs to store all these zettabytes. And if you think that each CD is 1.2 millimeter and you stack them one on top of the other, well, we'll reach the moon. We'll go beyond the moon. So you imagine a tower of CDs collecting all that data. That's in 2007, we would reach the moon. It's incredible. So another paper came later, and they said, well, forget about that data. If I look at just the healthcare data now, I forgot which year that this was, like I think 2015 or something like that. And they say we don't look at CDs anymore, we look at DVDs. And if we put the data in DVDs, then we'll reach the moon twice. So it's interesting because in between the 2 years, the two papers, there were only 4 years or something like that. And in 4 years, it doubled. Now look at this other image of, representing the space that we have available to store all sorts of data. In 2005, a micro SD card was the best micro SD card, had a capacity of 128 megs. In 2014, reached 128 gigs. And then it doubled in 2016, so 2 years later. Today, or actually 2 years ago, you can buy a micro SD card with 1 terabytes. So we're not talking about gigs anymore. And that means you don't delete images anymore. When you have a digital camera, in the past, very quickly you reach the full capacity of your SD card. You have to think, oh, which image I have to delete? Who deletes images today? So the improvement in 14 years is 8,000 times. So we went from 128 megs to 1 gig in just 14 years on the same space. Okay, this is a vintage kind of picture taken in 1956. In 1956, IBM was selling hard drives to some very fortunate clients who were able to buy computers at that time. And this is a hard drive being shipped to a new customer with 5 megs. 5 megs is just 1 image today. 5 megs was $120,000. Even the captain of the airplane was there for the picture, for the photo op. They climbed there just for the picture. It was so important. 5 megs. Well, today you can buy a 64 gig. This is in 2018, the price of 2018, $18. Recently, I don't know if I have another, I will have it later. I mean, you can buy it for less than that. But the interesting thing, if you look at this 64 gig in 2018, if you had that available in 1956, it would cost $1 billion if you look at this price of 120. It's unthinkable. So there's an improvement in 62 years, or more than half a century, but it's an improvement of 76 million times in terms of price. And that's why it's so cheap that we don't delete, we store everything we can store, we just store it. We say that storing is free. So cheap, it is free. Now, in terms of advancement in high performance computing, do you know what this is? This is called the GPU. It's a graphical processing unit. You have it, typically the graphical processing unit was put in a computer to deal with the graphics on the screen. Now they are becoming more and more sophisticated because people use them for playing games on the computer. And a GPU, this is a Titan GPU, it costs about $1,000. But the power that you have in a GPU is equivalent to a Cray 1 machine that, well, a few years ago, this was embargoed on many countries because it's so sophisticated, people use it for military usage. But, well, now it's a commodity. You can buy it in any store and put it on your commodity computer at home. So some people are building a graph, started in the early 90s, of the best computer or best computers every single year to plot here the progress. And this, note that this is, so you have time on this axis, but on this axis you have the power in terms of number of floating point operations per second. And this is a logarithmic scale, okay? So it's going up exponentially. The improvement is going up exponentially. So one of the last few years, in 2016, and for many years, the Chinese had the fastest computer with 94 petaflops. So these are a large number of operations per second, and it cost $275 million. Only recently, in 2018, the Americans were able to beat the Chinese finally, and by almost an order of magnitude here. Remember, these are exponential. And this machine was very expensive, and it's based on GPUs. It's have hundreds and hundreds of thousands of GPUs. Actually, they beat that in 2020 last year. I don't have the measures for this year, probably actually above the 200 petaflops. The Japanese beat the Americans recently with a new computer at the end of 2020. Again, I don't have the numbers for this year, but you can see they doubled the performance of the Americans. But the interesting thing is, so you look at these computers here, compared to the human, these computers have millions of CPUs. We have 90 billion neurons. So orders of magnitude more than these computers. But the more interesting thing, these computers require a lot of power, electric power. So we're talking about 28 megawatts. The brain uses barely 12 watts, so less than a light bulb. So there's a huge, huge difference in a lot of, I mean, we still have a lot of room to improve and get close to what the brain can do. The other interesting thing, I told you the AI is in your pocket, the small phones that you have. Well, those phones are actually getting quite impressive. They're comparable to the power in terms of how many operations per second. It's comparable to the fastest machine in the late 90s. But the fastest machine in the late 90s was costing $55 million, was the size of a tennis court, and used 850 kilowatts. It used the energy equivalent to 800 houses. Now you have it, well, where do you have it? Check what's on the desk here. You have it on your cell phone. That whole room is now in your cell phone in just a few years. We take it for granted, but that's phenomenal progress. And this is exactly what is happening now with the computers. Today, these big computers allow us to run, sorry, I have this somebody calling. I'm turning off. Good, sorry about that. These computers are able to run those algorithms that I mentioned briefly, that were designed originally in the 50s, but we didn't have these computers. Now we have these computers, we can run them, and we can do amazing things in AI. This is to show you, this is the fastest computer in 93 when I was doing my PhD, and the difference with this computer in 2018, in terms of progress in just a few years, it is equivalent to how many times? 206,000 times in 25 years. In 25 years, computers have improved 206,000 times. What does that mean, 206,000 times? It means that if I, as a human being, was able to do the same kind of improvement on my own, okay, I would be 206,000 times better than what I was in 1993. That means that if I improve 206,000 times, that means that if I used to do one step, 1 meter, let's say, well, today my one step would be 206 kilometers. I would be able with one step, if I progress the same way as computers, I would be able to do in one step, I would almost reach Calgary. I mean, this is ridiculous, but that's exactly the analogy with the progress that computers have done. And if I look at the progress in terms of storage, with one step, now I can do almost 8 kilometers. Okay, so 8,000 times. The progress in terms of price, I would be able to, with one step, I can go around the earth twice or more. Okay? That's how you can realize Actually, it's even cheaper. And this is in 2019. Or anyways, the costs are even cheaper. So I can go even more around the Earth. And this gives you an idea about the progress. And now if you go backwards and see like from the early days of the computers in 1946, then it's unfathomable the kind of progress we have. This is the first general computer in Philadelphia after the Second World War. There's another, the Zeus. This is during the war. This is by the Germans. It was doing 1,000 floating point arithmetic operations in an hour. They were talking about an hour. So it's really, I'm telling you, we're taking it for granted. So in terms of progress, that's for the high performance computing and for the data that we are collecting, but also the algorithms are becoming more and more sophisticated. So I'll drill a little bit more. So I mentioned the fact that we're using technology that we thought about in the 50s, artificial neural networks. Now we call it deep learning because we're able to put way more layers, and because we can now try different architectures. We have the luxury to use a lot of data, and we have a luxury to use these computers to try different architectures. And when we tried these different architectures, we were able to do amazing things. So what is deep learning? Basically, deep learning is like this artificial neural network, multi-layer perceptron, we call it, that was imagined and devised in the 50s. Basically, they are simulating neurons in the brain. Neurons are cells that are connected to other neurons. They receive a message through the dendrite with different strengths. And at one point, the cell will send a message through the axon and reach different other cells. So here we have artificial cells, units here, that are organized in layers, and they receive a message from the previous layer and pass it to the next layer. So in the early days, when we were talking about artificial neural networks, typically we had only 3 layers. We have the input layer, the hidden layer that you don't see, and the output layer that will do the prediction. What happened with these, as I said, with these sophisticated computers, we can try now different architectures, and we're able to add as many layers as we want. Now we have actually thousands and thousands of these layers. And that's why we call it deep. It's deep learning. Okay, and there are many different kinds of architectures for different purposes that allowed us to do very sophisticated things. The interesting thing about this for us here in Canada is the fact that for years people have kind of forgotten about artificial neural network, but pioneers kept on working on that, like Jeff Hinton from the University of Toronto and Yoshua Bengio from the University of Montreal. And thanks to their perseverance and stubbornness, we have the AI that we have today. So Canada is a huge contributor to the AI in the world. Of course, there are other people from Switzerland, like Jürgen Schmidhuber and Jan LeCun, who is the head of AI at Facebook. But Jan LeCun was actually a postdoc of Jeff Hinton. So what happened? So why deep learning came to the surface like this? There is a competition that started in 2009, where you have 14 million images from many different classes. So we have plants, animals, devices, buildings, humans, food, whatever, you name it. And the competition is about writing programs to automatically classify these and recognize which plant it is, which animal it is, and so forth. So this is a plot showing the winner of each year. You can see that the accuracy was 70%, and then it started going up in the year after. They improved 71%, the year after 74%. In 2012, students from Jeff Hinton won, but everybody was expecting it to reach something around here, but it jumped to 83. So a huge, I mean, 1 order of magnitude here. People were surprised, say, what did you use? And he said, oh, I'm using GPUs and neural networks. Actually, we call them deep learning, deep convolutional networks. And that's what made everybody focusing now on deep learning. And they realized that they can do a lot of things with it. Just for this, just an example, for this task, typical humans, the accuracy of typical humans is around 85 to 90%. Experts who are really good at these images are in the 95% accuracy. Year after year with deep learning, now we do better than the expert humans at distinguishing between animals, plants, and person and food within these pictures. They're not necessarily easy. So they said, okay, what can we do apart from recognizing these images? Can we do something else? By the way, Google was immediately interested in this, and they hired the students and Jeff Hinton with Google to now recognize cats from dogs and other animals in their search engine. But they said, okay, can we use it for something else? Can we use it, for example, for speech recognition? There's another competition, very famous competition that started in the 90s. This is funded by DARPA. DARPA funds research typically related to defense and military. They have, so this is a switchboard data set. They have a lot of data of recording of conversations on the phone, and they want to be able to automatically transcribe it because they can't ask people to listen to this and type it all. It takes too long. How can we do it with machines? And for years, people have been trying. This plot is different. This is measuring the error rate, so the lower the better. And they were plateauing for years until we started using deep learning, and now we're doing actually better than humans at transcribing recordings of voice recording into text. And then they tried it for object detection in images, and we do better than humans. They tried it on automatic translation. We're not as good as humans, but you can see after the use of deep learning, it started skyrocketing here in terms of performance. Same thing with visual query answering, question answering. Like this is we're getting very close to human performance. This is like the text comprehension in high school. But even though it looks amazing, there's still so many problems. If I show you this picture, what do you see? I'm just seeing if you are still following me here. What do you see here? Who can tell me what's in this picture?
A desert.
Yeah, the desert.
Desert, yes, desert. What else can you say?
Sand.
Sand, desert, sand, dunes. Okay, well, this image was given to a program based on deep learning that the police in the UK was using to identify pedophiles and child abuse. And this was labeled and flagged as a picture of nudes. Why? Because, well, the color is very close to skin color or something like that. So you can see we can still make errors. Humans will never say this is a human skin. So even though we claim, hey, these machines are doing better than humans at detecting a cat from a dog or whatever, they're still making very silly mistakes. Here's another example. Who can tell me what this is? What is it?
Red Ferrari.
A red Ferrari. Have you ever seen it before in real life? This one, this model?
Not that specific one.
Exactly. So you have never seen this picture, yet you were able to identify that is a Ferrari in a red Ferrari, and it's a car. Why it's not an insect? I mean, it looks more like an insect than a car. Well, do you know what a deep learning algorithm would tell you? They'll tell you it's a horse. It's not an insect, it's not a car, it's a horse. Why? Well, there's the Ferrari horse there. Well, let's turn the car. Now I can see the wheels. And maybe by analogy, because I see the wheels, I can say it's a car with confidence. Okay? Well, the deep learning can tell you, well, it's a horse. Actually, it's more than a horse. I have many horses there. Okay? These are silly mistakes that humans would not do. Here are other, this is impressive actually, automatic labeling, but still making silly mistakes. The deep learning will say, looking at this image and analyzing this image and describing it, it'll say a soccer player is kicking a soccer ball. So it recognizes a soccer ball, recognizes a soccer player, which is amazing. But certainly the soccer player is not kicking the ball. He's standing in front of the ball. Here, a street sign on a pole in front of a building. It's actually not in front of the building. If we look carefully, you can see that the building is far away. It's on the other side of the street. So the computer doesn't see the depth in this case. Here again, a couple of giraffes standing next to each other. Are they? Actually, one is far away from the other. Probably a few meters, 20 meters or something like that. So there's still some silly mistakes. Here's another tough one. Where's the dog? Where's the puppy? Where's the bagel? It's a pity that I don't see your faces smiling, laughing or not. Well, here's another one, even more complicated. A Chihuahua with muffins. Is that a muffin or is that a Chihuahua? And now if I put them both in the same picture, that'll be tough. Well, there are many like this that are not easy, even for humans sometimes. Watch out which one you think is a chicken and try to bite it, because it'll bite you back. What about this one? Is that a mop or a dog? Well, that led to a field where we try to fool the computer. Fool the computer because now computer vision, which you're using AI, computer vision is becoming very important. Like, for example, self-driving cars. The self-driving car has to recognize signs, whether I'm allowed to turn left or right, or have to stop or reduce speed, or things like that. And people can play with these signs and put stuff on it so that the cars don't recognize it. So here is an example. This is a picture of a panda. And the computer will recognize the panda with some confidence, like 57.7% confident, this picture here of the panda, because I don't see the panda completely, it's cropped, okay? But I have some confidence it is a panda. If I take that picture and I add some noise, okay? Some noise, you don't see it very well, but it generates this image. And I pass the same, for us humans, it looks at the same image, it's the same image, but actually the pixels are not necessarily the same. The computer now suddenly recognizes a gibbon. A gibbon is this animal because it's focusing on this part of the image or something, and it's the face of the gibbon. It doesn't recognize the panda anymore. Here's another example. This is a banana, and the computer, the classifier says it's a banana with high confidence. It may be a slug, it may be a snail, maybe an orange, but I have very low probability. And high probability is a banana. Then on that image, I will add some kind of bizarre drawing, looks like a cell with a Golgi apparatus and a nucleus and stuff like that, and just stick it on that image and give it to the computer again. The computer will say, well, I think it's a banana, but I'm not sure. Maybe it's a piggy bank, but I'm not sure. But I'm very sure it's a toaster, because it looks like a toaster from far away. Why a piggy bank? Maybe because of these slots or something like that, but it doesn't recognize the banana with very small confidence. So it's very easy to attack these algorithms to fool them. Okay. How much time? How am I doing with time? Oh, I have just 20 minutes. So what is this machine learning? Now, I said machine learning is part of AI, and within machine learning, we have this deep learning that allows us to recognize a lot of stuff like these images and doing the machine translation and question answering and so forth. So what is this machine learning? Machine learning basically provides this means to machines to learn from some data in order to adapt to the data. What does it mean, adapt to the data? Well, basically, it will build a predictive model to do predictions. So it learns from experience, like we were trying to define intelligence. We talked about experience and applying the experience that we learned in the past in the present. So it learns from experience in order to predict. And what is this prediction? The prediction is basically adapting to new data, a new environment that is given to it, to predict what to do or what it is and things like that. So in the field of machine learning, there is deep learning. It's one of the methods, one of the paradigms of supervised learning, but supervised learning, it means it requires some training data, it requires that experience, but there are many other approaches as well. So in a nutshell, if I want to visualize it, it looks like this. I have data that is given with labels to train. The algorithm went through it and picked up some trends in the data, some patterns, and builds a classification model. Then I have, that's the past. The training set is the past, my experience. Then I have new data that I have never seen before, which represents the present. I will use this classification model and I will predict their labels. So I learned from the past the labels, what discriminates the green from the red, from the blue, from the black, and that's my model that I built here. And I'll show you later what's in this cloud in the third part of the lecture series. But right now, just imagine this is just a cloud. It's a predictive model. It's used to predict the new cases by labeling them automatically. That's what we call supervised learning. That cloud that I represent here could be a neural network. Okay, the neural network is one example of what can be in that cloud, and I would use the neural network to label these. So the neural network will have a representation of this training data within it in order to predict. There are other techniques for learning, like reinforcement learning. The University of Alberta is the mecca in the world for reinforcement learning because we have one of the pioneers in the field, Rich Sutton. I don't know if this year he will talk to this class, but in the past he has done so. He's here at U of A. But AI is way more than just this deep learning, okay? But deep learning allowed us to make huge strides forward in some applications anyways. So why deep learning is particular compared to other methods? I said there's so many other methods. The reason is that when you add, so this plot, how to interpret this plot. So basically when you add more data to the algorithm, you can see that the performance gets better and better. So the more experience it sees, it gets better and better and better. But most of the other algorithms, they will reach a plateau and it's like they don't know what to do with the extra data. However, deep learning keeps on learning. And that's why at one point it reaches the performance that humans have and can surpass the human performance. So what are examples of this machine learning? Examples of applications. I mentioned briefly spam. Spam detector in your email application, your email client, typically use machine learning because it adapts to you. It observes you, what email you read, what email you delete, what email you store, and it learns from that experience. It builds a model that models your behavior. It learns what is considered a spam for you, what is not a spam for you, and will, after a while, when the accuracy, when the confidence goes up, it will do it automatically. It labels it automatically, means it'll put it directly in the spam folder without bothering you. And it adapts to you because what is spam for you is not necessarily spam for somebody else. And what is spam for somebody else is not necessarily spam for you. Another application is credit approval. When you go to the bank and you ask for a loan, typically there's a program in the background that looks at your characteristics. Do you own a car? Do you own a house? Do you what kind of diploma you have, how old you are, and things like that. And it learned from its experience meaning looking at other customers who paid the loan, who didn't pay the loan, and it learns a model to predict for you whether you will be paying back the loan or not. And if it predicts that you will not, then it'll say, no, it's rejected. They're used in the background. Machine learning is used in the background in some financial institutions. It's used also in credit card transactions when you swipe your card and the merchant is sending an requesting an authorization for that transaction from the institution, the bank card institution, then there is an algorithm that is running in the background to look at your purchasing behavior to see if it can predict that purchase or not. So is it fraudulent or is it legit? And in a fraction of a second can respond, yes, I'll permit this or I don't permit that. There are many applications in medicine for diagnosis, for prognosis, recommending treatments. So precision health, precision medicine, machine learning is the major pillar. There are many other applications. I don't know if I have time to talk about this. I can go back to this later, how you make a wheelchair automated for paraplegic people. You can also control a cursor on the screen automatically based on the brain activity. You can control it to go left, right, up, down, and then you can select the letters. and so the paraplegic is able to actually write messages on the computer without touching anything. I mentioned reinforcement learning. Reinforcement learning is a completely different kind of learning. It's based on trial and error, behavioral learning. You do actions, and those that work, you continue to do them, and those that don't work, you don't do them anymore. Like training a dog. You say roll, it doesn't roll, you don't do anything, you say roll again, roll again. The day the dog rolls, you give it a treat. And then it says, oh, when I roll and they say roll and I roll, they give me a treat. So I want to maximize my treat. And I'll do it again each time they say roll. And that's how they learn. So basically you have an agent. Here I'm representing with a robot. It's just a software. And you have the environment. The agent has a set of actions it can take. I'm representing them here with tools. It will select one, let's say the hammer. It'll use that action. And then there you have an observer that says, ooh, because you use that action, the environment changed this way. So here's the new state of the environment due to this action. And by the way, here's a reward. And this agent is trying to maximize the reward that it can take after doing these actions. Okay, it will end up doing only the actions that, so that the policy that it learns here will ensure that it takes the actions that will maximize that reward. That's how it learns. And one of the pioneers, or the pioneer, I would say, of reinforcement learning is Rich Sutton here at the University of Alberta. And that technique is used in robotics. Here we have adaptive prosthetics. We have a lab, Blink, that is led by Dr. Patrick Pilarski. And again, in the past, he was giving a talk at this class. I don't know if this semester he will also.
He is. Yeah.
Cool. So the technology that he's doing is based on reinforcement learning. Basically, that's the feedback from the user, and that feedback is coded into some kind of reward, and you have an algorithm that is trying to maximize the reward. And what happens is that rather than just the patient is getting used to the prosthetic is also adapting to the patient. I think I reached the end, and I want to give you some time for you to ask me questions. So that's it for today.
Great. Okay, any questions? Do you want to unshare so that we can see the people bigger?
Sure. Stop sharing is here.
There they are. Yeah, in all their manifest glory. Okay. Okay, questions? Comments?
So I can tell you about the paraplegic. Well, ask me a question about the paraplegic wheelchair. How does machine learning make it automated? I'll explain. Oh, you have other questions? Please do.
I have a question about reinforcement learning. So if we're the ones that are reinforcing the algorithms when they do something correctly, does that mean we can, like, it's hard for them to do the wrong things or go against us if we're the ones reinforcing them? Like, would you agree with that?
Well, it depends who is reinforcing them. It can be us, or it can be in the environment itself. So for example, I'm a robot and I need to go to the door because I need to go to the other room. And I have different actions I can take. I can go forward, I can go to the left, I can go to the right, I can go to the back. But if I go to the right, I will hit the wall. And if I hit the wall, then I get a negative reward, let's say. Okay, because I was not able to reach, I wasn't able to get closer to that door. So it's not always a person sitting next to that agent to give it the positive reward or the negative reward. The environment itself, now what I represented as the observer in the environment, the observer is not necessarily a human being. It can be, well, another program will give it that reward.
Okay.
And the reward, that's what people were asking me, because when you dealing with an animal learning with reinforcement learning, like a dog for rolling or giving the paw or something like that, or even the child, when they do bad behaviors, say, no, that's not good. When they do good behavior, we'll give them a sweet. That's a reward as well. What's the reward for the computer? Well, the computer is basically adding up ones and zeros. And it's a number that they will get, and they want to maximize it. The bigger the number, it's like being on a leaderboard. I want to get more points. I play more to get more points. It's the same thing. So the reward is not a cookie or a slap on the hand. It's a number, an arbitrary number.
So other questions?
I have a question. So what all the AIs that we've been looking at so far have been AIs operating in their very kind of specialized environments, like image recognition or natural language processing, things like that. But we as humans do all of it all in one kind of machine, you could say. Are there any initiatives that you would know of that kind of look to merge a lot of these very specialized functions and kind of create these more composite algorithms that do all of these functions or some of them all at once?
That's a very good observation. And it's something that I will address next time we meet, which is next week. We humans are very versatile. We can do many different things at the same time. I can play chess, I can draw, I can cook, I can read a book, I can recognize a cat and a dog. I'm the same machine, I'm the same person. But computers, you have a computer that is specialized in playing chess and doesn't know how to do anything else. This algorithm can recognize a cat from a dog, but it doesn't recognize this disease from that disease. I mean, they're very, very specialized and very good at doing what they were designed for, but nothing else. Yes, there are initiatives to create what we call an artificial general intelligence. So it's not really specialized, it can do other things. And this is one of the goals of a company like DeepMind. You probably heard of DeepMind. DeepMind started in London, UK, and they now open in other places. The first place they open outside the UK is here in Edmonton, particularly because they're very interested in reinforcement learning. So DeepMind is interested in building a program that can do more than just one thing. And they proved it with, and I'll mention it next time, the program Alphago. You heard of the program Alphago?
No, never.
So Alphago is a program, I'll go into further details next time. It's a program that plays a game called Go. Go is very, very difficult actually to program. It's very easy to play, even kids play it, but it's very difficult to program a machine to play it because the search space is huge, is way bigger than chess. And computers were not able to beat even kids. And suddenly, with work that actually started here at U of A and improved upon that within DeepMind, they were able to beat the best of the humans, the world champion, and actually created a shock around the world. That program, Alphago, to play Go, was able to learn afterwards, not from past games, but it was able to learn by playing against itself. So they didn't give it anything about the rules, and then it played against itself, and it learned how to play, and it beats the best in the humans, best player. Then they said, okay, well, let's remove the rules of Go and put rules of something else like chess, and was able to learn in a few hours how to play better chess than the best program at chess. I'm not talking best humans, because the chess, the computers beat the Garry Kasparov in 1997 already. So we're not talking about humans anymore. So this program that learned to play against itself in few hours was able to beat the best program in chess. The same one that was learning to play Go. So here we are at the first steps of building programs that can specialize in different things at the same time, not just one thing. We're not there at the level of humans to be completely versatile, but there are many initiatives to go in that direction. Did I address your question?
Yeah, it's got my mind flowing. I'll think about this for next time. Thank you.
Yeah, sure. We are an incredible machine. The humans are an incredible machine. And we are discovering more and more how complex we are.
Other questions?
I just had a quick question. Could you maybe elaborate on how a machine-brain interface works non-invasively?
So the one that I mentioned briefly for the wheelchair, for example, or the cursor on the screen to select letters. Basically, we wear hats with electrodes to get the brain activity, electrical brain activity. And we tell the patient to think about something. For example, in the case of the paraplegic patients, we tell them to think about moving the right thumb. And we ask them to do that many times and look at the signal that we receive from the electrodes in that hat. And we learn to detect that signal from other signals. And we attach that to turning the wheelchair to the right or turning the cursor to the right. Then we ask them the same thing to move, for example, think about moving. They can't move because they are paraplegic, but just thinking about moving the left toe or the left knee or something like that. Each patient is different because the signals are not captured the same way. And once we get that pattern, we attach it to turning the wheelchair to the left or stopping or whatever. So different thoughts attached to different actions. And there you go. Now you have the paraplegic sitting on the wheelchair and thinking about, I don't know, wiggling their left toe, and the wheelchair moves forward or stops or turns left or turns right. Same thing with the cursor. And the military basically are using this as well for the pilots in the fighter jets to also have more than just two hands to control the different things that they're doing. And they have this monitor on their visor of the helmet, and they can do other things by thought as well.
That's amazing. Thank you.
Welcome.
Other questions?
I just had a quick follow-up to that question. So just given the amount of noise or lack of sensitivity to surface level electrodes, is there a future in non-invasive EEG prosthesis, or will we have to move towards more invasive brain-computer interfaces?
Well, there are many people who are thinking about more invasive ones where they put the electrode right inside. It's more expensive. The results are better for sure, but it's more expensive. There are risks as well. So there are many other people who are still interested in this non-invasive approach, even though there's a lot of noise. And that's why different patients, you have to train them with different kind of, this one you say, move your left toe, while the other one you say, move your left finger or elbow or whatever. Because of this noise, it's not the same from one patient to the other. It's not really consistent. And it takes longer to train, I guess. But the results are satisfactory for those applications. So why adding an invasive kind of electrode inside when you can do it without?
Yeah, thank you.
Welcome.
Okay, well, that's a great teaching session, and we look forward to the 2 more next week.
Thank you.
Yeah, the week after, we have Michael Van Manen doing ethics of the future. And then Patrick Pilarski is after that, and possibly Rich Sutton then, or perhaps later in the course. I think he is going to teach in the course. I'm just not absolutely sure the date. Yeah. So, okay. Thank
you for your attention, guys.
Very much.
See you next meeting.
Okay.
Bye.
Bye-bye.
Thank you.
Bye.
Thank you.